Excuse me. Alrighty, well, hello and good evening. Welcome to lecture. Excuse me. We're going to be picking up where we left off. So on Thursday, we had just begun introducing the topic of stoichiometry. We said that this was a challenging topic, so hopefully you spent some time practicing over the weekend. I left you with a problem to try, kind of the next step, next level. So now let's give it a whirl. Let's determine the number of molecules in a 2.0 gram sample of ammonia, which is NH3, nitrogen trihydride. Now, where, excuse me, where this problem differs from examples that we've done previously is before I'd give you a sample of 5 grams of copper or, or oxygen or an atom, an element. I'd ask you to determine the number of atoms present, but this is a molecule. If I told you had 5 grams of copper, you look up the atomic mass of copper on the periodic table, and use that to convert from grams to moles, and then you convert from moles to atoms. But there is no box for ammonia, NH3, on the periodic table. And so we have to do one additional thing. We can't look up how many grams of ammonia are in 1 mole, but we can look up how many grams of nitrogen are in 1 mole. There's 14.01 if you look it up on the periodic table, grams per mole. And you can look up how many grams of hydrogen are in 1 mole. It's 1.008 grams per mole. And so we're going to have to calculate this ourselves, how many grams of ammonia are in a 1 mole sample. And the thing you've got to remember, you got to keep in mind are the number of atoms. So we don't just have 1 hydrogen here, we have 3. So we're going to need to multiply this by 3 and then add these two quantities together. And when we do, the name of the quantity we calculate is called the molecular mass or molecular weight. All right, so we need to calculate this conversion factor for ourselves and then use it to solve this problem. So first off, let's calculate the molecular weight of ammonium. Sorry, of ammonia. Nitrogen has an atomic mass of 14.01 grams per mole. Hydrogen has an atomic mass of 1.008 grams per mole. And again, you get both of these values by looking them up on the periodic table. Because we have 3 hydrogen atoms in ammonia, we need to multiply the atomic mass of hydrogen by 3. Right? Then we add these two together. And 1.008 times 3 is 3.024 plus 14.01. This comes out to be 17.034 grams per mole. When you look at the sig figs for this number, 1.008 has its last significant digit in the 3rd decimal place. 14.01 has its last significant digit in the 2nd decimal place. So this number's last significant digit needs to be in the 2nd decimal place. So I'm going to put a line there to remind myself that this value has 4 sig figs. All right, now we're going to use this to calculate how many molecules of ammonia are in a 2-gram sample. So you have 2.0 grams of NH3. In our first step, we need to convert from grams of ammonia to moles of ammonia. And this is where the molecular weight comes into play, because that tells us, and let's see, I've already forgotten what it is, so I'm going to just take a peek, 17.034, that there are 17.034 grams of ammonia in 1 mole, and the last significant digit in this number is in the second decimal place, so this number has 4 sig figs. You'll notice that grams of NH3 cancel with grams. This leaves us with moles of ammonia. Now, we haven't been asked for how many moles of ammonia are in a 2-gram sample. We want to know the number of molecules. And remember, Avogadro's number allows you to convert from moles to things. And in this case, so we put moles of ammonia in the denominator. In the numerator, we put molecules, because ammonia is not an atom, it's not an ion, it is a molecule. Now, in a 1 mole sample, there are 6.022 times 10 to the 23rd molecules. And again, I recommend putting that down on your exam sheet, because you want that at the ready. Now, moles of ammonia cancel moles of ammonia, and we're ready to crunch some numbers. So we have 2 divided by 17.034 times 6.022. Hang on, sorry, I messed up my calculation. 2.0 times, no, not times, divided by 17.034 times 6.022 times 10 to the 23rd. So the value that I'm getting from my calculator is 7.0705648 times 10 to the 22nd molecules. Of ammonia. And now we have to ask how many sig figs. Our molecular mass has 4 sig figs. Avogadro's number also has 4, but our initial mass only has 2, so our answer can only have 2. So we count off our first 2 sig figs. 7 will round up. And so 7.1 times 10 to the 22nd molecules of ammonia are contained within, excuse me, a 2-gram sample. So that is the answer for the question that I left you with on Tuesday of last week. All right. Let's do another example. How about we give the following example a try. How many molecules of water let's see, where's my, oh, there we go, are contained in a 150.00 milliliter sample. And note that the density of water is 1.008 grams per milliliter. All right, now this is a great example for this is a great practice problem because we've never done a problem like this before. Not exactly like this before. It's similar to other problems we've done, but we've never worked this exact thing. And I guarantee you on the exam, you will encounter problems unlike problems that I've done in lecture, unlike problems from the assigned homework. It'll be totally new, totally fresh. Now, this is great practice for that. So I'm going to show you how you tackle a problem that you've never seen before, never done before, but I'm going to give you the tools for solving a problem that's brand new, and that will pay dividends for you when you take exams in this class, because there will always be problems that I haven't done, because I'm not testing you on did you memorize how to do a problem. I'm testing you, did you understand those problems? Are you able to problem solve in a unique context to demonstrate your knowledge of chemistry? All right. So how many molecules of water are contained in this sample with this density? The first thing you want to do whenever you're solving a problem is identify what you're trying to find. All right, and we want to know the number of molecules of water. All right, we want to find the molecules of water. That's step one. Step two, identify what you're given in the problem. Because what you're given in the problem, you're given enough information to find what you're being asked for. So start by identifying what you're given. First, you'll notice that we're given a volume of water. All right. We're told that we have a 150 milliliter sample. All right. We're given another piece of information. We're given the density of water is 1.008 grams per milliliter. Now, this is not explicitly in the problem, but this is something that you need to be aware of, because this is clutch for any STEM class, but especially chemistry, physics, classes like these. You'll notice that you were given a quantity for density. Density has an equation, has an algebraic expression associated with it. And whenever you're given a quantity that is part of a bigger equation, you want to write that equation down under your given information. The equation for density is something that you'll want to have on your exam sheet, or you can memorize it, but I recommend putting it on your exam sheet. And density, the equation for density, is equal to the mass of a substance over its volume. And you'll notice in our given information, we're given density, we're given volume, so that allows us to solve for mass. Now, that's what these two pieces of information allow us to do. With volume, with density, we can find our mass. Does mass connect to the number of molecules? Well, as we know, we can calculate a molecular weight to get a unit conversion to convert from grams to moles, and then the unit conversion from moles to molecules uses Avogadro's number. So we know that we can take our mass and find moles. And once we know moles, that'll lead us to molecules. All right, so that is a roadmap forward. That is how we're going to attack this problem. Step number one, we need to do some algebra to find the mass of our sample of water in grams. So density is equal to mass over volume. We need to solve for mass by multiplying both sides of this equation by volume. So we get a new expression. The mass of our sample of water is equal to its density times its volume, and we know both of these quantities. Our density is 1.008 grams grams over milliliters, and then our volume is 150.00 mils. So milliliters cancel, and we get a mass. Let's see, I gotta punch this into the calculator. 150 times 1.008 comes out to be 151.2. Now we have to ask ourselves, how many sig figs can we have? You'll notice that our density is 4 sig figs. Our volume has 5. So we're limited to 4. And the cool thing is we actually don't even have to round here, because 151.2 already has 4 sig figs. So we don't need to add any zeros. We don't need to round. It's good the way it is. And our units here are grams, specifically grams of water. Now, what we need at this point, we weren't asked to find grams of water. We need to find molecules of water. So we want to convert from, we can't convert from grams to molecules, but we can convert from grams to moles. And then once in moles, we can convert from moles of water to molecules, because 1 mole is 6.022 times 10 to the 23rd. All right, let's see, that's H2O. So we know the conversion from moles to molecules, but we need the unit conversion from grams to moles. And for that, we got to calculate our molecular weight. Hydrogen has an atomic mass of 1.008 grams per mole. And we have 2 of them in this molecule, so we got to multiply that by 2. Oxygen has an atomic mass of 16.00 grams per mole. So we add these 2 together. Let's see, 1.008 times 2 plus 16 is 18.016 grams per mole. We have to round. Our last significant digit has to be in the second decimal place, because 16.00 has its last sig fig in the second decimal place. So I'm going to wait to round to the end of the problem, but I'm going to remind myself that this number 18.01 only has 4 sig figs. All right, now grams of water cancel grams of water. Also, moles of water cancel moles of water, and we are ready to crunch our numbers. So 151.2 divided by 18.016 times 6.022 times 10 to the 23rd. Oh, wow. Hang on. 18.016. This has 4 sig figs. Okay. So, my number is 5.053987. 6. No, it's not a 6. It's a 5.7, unfortunately. Almost, it's a 6 if we round it. Times 10 to the 24th molecules of water. All right, and we're limited to 4 sig figs here. So count off 1, 2, 3, 4. 9 rounds up. So our final answer is 5.054 times 10 to the 24th molecules of H2O. All right. So that is the number of water molecules contained in a 150 milliliter sample. All right, now these problems are good. They're good practice, they're good warm-up, but they're not the meat and potatoes of stoichiometry. All right, you're definitely going to run into them in an exam context, but we're about to transition to what stoichiometry is actually good for. All right, let's go back and revisit an equation that we've seen a few times already in this class, the combustion of hydrogen gas. All right, there are a couple ways we can read this equation. Brandon, it's just a result of the multiplication or division going down in each problem. All right, so looking at the combustion of hydrogen, there are a couple ways of reading this equation. One way you could read this equation is you could read it as 2 molecules of hydrogen react with 1 molecule of oxygen, right? Because there's a 1 here, to produce 2 molecules of water, right? That's one way we could read this chemical equation. 2 molecules of H react with 1 molecule of O to produce 2 molecules of H2O. Another way you could say it, you could say that like 2 dozen molecules of hydrogen will react with 1 dozen of oxygen to produce 2 dozen molecules of water. You could read it that way as well. That wouldn't be particularly useful. I wouldn't recommend reading it that way in particular, but I'm doing it to illustrate the point that what's actually going on in a balanced chemical equation is these stoichiometric coefficients, though they do tell you like, oh, 2 molecules of this one, 1 molecule of this one, make 2 molecules of that one. But they actually represent, their real utility comes in the fact that they represent the number of moles of each reactant and product that is reacting or being produced in the reaction. So 1 mole of H2O reacts with 1 mole of O2. Sorry, 2 moles of H2 react with 1 mole of O2 to produce 2 moles of H2O. All right, that is the key to understanding these relationships. So, for example, I could ask you the following question. How many moles of H2O of water are produced when 13.0 moles of oxygen react? To answer this question, you need a balanced chemical equation, all right? And here's how you answer it with the balanced chemical equation. We're told that 13.0 moles of oxygen react, and we're asked how many moles of water, right, are produced. We need a unit conversion that will convert moles of oxygen to moles of water. Where can we get such a thing? The answer is that exact unit conversion is contained in your balanced chemical equation, because your balanced chemical equation tells you for every 1 mole of oxygen that reacts, 2 moles of water are produced. So the ratio that you add, the numbers that you add to this ratio, is 1 mole of oxygen and 2 moles of water. You'll notice that moles of O2 cancel. Now we crunch our numbers. When you multiply 13 by 2, your calculator will tell you that your answer is 26. But we need to have 1, 2, 3 sig figs, so we need to add a 0.0. 26.0 moles of water are produced when 13 moles of oxygen react. All right? Let me ask you. So that was a warm-up question. All right? The questions that I'm actually going to ask you on the exam will look more like this one. Here, let me move our equation up so we just have a little more room to breathe. So can you do an example like the following? How excuse me, how many grams of water are produced? How many grams of water are produced when 1.0 grams of hydrogen react completely? Question. All right, now, this is the #1 mistake to watch out for. It's very, very easy to make this mistake, to go, oh, well, you'll notice that the ratio here between hydrogen and water in this chemical equation is a 1-to-1 ratio. So you might look at this and think, oh, well, 1 gram of H2 reacts, I should make 1 gram of water, and that would be incorrect, because this is not a mass ratio, this is a mole ratio. It doesn't tell you that 1 gram of hydrogen produces 1 gram of water, it tells you 1 mole of hydrogen produces 1 mole of water. So you have to convert from grams to moles if you want to use the built-in unit conversion inside your chemical equation. All right, so always, first step, stoichiometry, always going to be converting grams to moles. Speaking of which, let's do so right now. 1.0 grams of hydrogen. Our first step needs to be to convert from grams of hydrogen to moles of hydrogen. Now, if you look up H2 on the periodic table, its atomic mass is 1.008. We have two of them in this molecule, so it'll be 2.016. Grams of hydrogen cancel grams of hydrogen. And now that we're in units of moles, we can use the unit conversion given to us by our balanced chemical equation to convert moles of hydrogen to moles of water. So 2 moles of H2 produce 2 moles of H2O. Moles of H2 cancel moles of H2, leaving us with moles of H2O. And finally, we were asked how many grams of water are produced. So we have one more unit conversion. We need to convert from moles of water to grams. And to do this, we need to calculate our molecular weight. Oxygen, when you look it up on the periodic table, has an atomic mass of 16.00 grams per mole. Hydrogen is 1.00, but we've got two of them, so 2.016 grams per mole will be the mass of hydrogen. I am so sorry. I am so sorry. I've been holding that sneeze in the entire class, and it just snuck out. I apologize if I peeked out the mic. I've been feeling a little under the weather, but the nice thing is there's no chance of contracting COVID over YouTube, right? It's actually very nice. 16.00 plus 2.016 is 18.016 grams per mole. My last significant digit is in my second decimal place. So this number has 4 sig figs. I need to wait to round till the end. So I'm putting these lines underneath to remind myself of my significant digits. 1 mole of water has a mass of 18.016 grams. 4 sig figs. All right, moles of water now cancel moles of water. And now we're ready to crunch our numbers. 1 divided by 2.016 times 2 divided by 2 times 18.016. My calculator is telling me that the answer is 8.93650794. However, I am going to be limited to 2 significant figures by my initial mass. 3 rounds down, and so my final answer is 8.9 grams of water are produced. All right. So that is the mass of water produced when 1 gram of hydrogen reacts. And I'd just like to point out, we said this earlier, that the 1-to-1 ratio is a molar ratio. But here you can see how wrong we were if you were tempted to say, oh, it'll make 1 gram of water. 1 gram of hydrogen made almost 8.9 grams of water. So you can't ever use these as mass ratios. They must always be molar ratios. All right. So this is your first proper stoichiometry problem. This is the type of thing that you'll be doing, excuse me, over and over and over again in this course. So this is what you want to practice. This is what you want to get good with. Let's see. There we go. All right. Let's do... hang on. Before we move on to the next problem. Whoa. Nope. There we go. Before we move to the next problem, this has a name right here. This is called our theoretical yield. So a yield is the amount produced, and this is the theoretical yield of water based on 1 gram of H2. With that piece of vocabulary under our belt, we can move on to solve the next problem. Next problem. Iron 3 oxide reacts with aluminum metal to produce aluminum oxide and iron metal. Part A, write a balanced chemical equation. For this reaction. Part B, determine the theoretical yield of iron the theoretical yield of iron metal if 5.00 grams of iron 3 oxide react completely. There's a whole lot going on in this problem. All right, there's a whole lot going on, but this is full metal stoichiometry. This is everything that you could be tested on, kind of rolled up into one. Well, not everything, but this is a full metal stoichiometry problem. Definitely the hardest one we've seen yet. So let's start with part A, which is write a balanced chemical equation for this reaction. It starts with having to figure out what our reactants and products actually are. All right, so starting with iron 3 oxide. Iron is a transition metal, right? In this, it's we don't know, we can't determine the charges of transition metals by looking at the periodic table, but we can, or we do know the charge because we're told, right? It's right up there in parentheses. In this molecule, iron has a charge of +3. Now, with oxygen, when you look at its position on the periodic table as an anion, has a charge of -2. Now, because 2 and 3 don't go into each other evenly, the way we get our molecular formula is for our cation, which is iron, we give it a subscript equal to our anionic charge. And for our anion, which is oxygen, we give it a subscript equal to our cationic charge. So iron 3 oxide is Fe2O3. All right, that is one reactant. Now, we're told that it reacts with aluminum metal. All right, aluminum metal is just aluminum, the element, Al. Nothing fancy there. We're told that these two react to produce aluminum oxide. Now, aluminum, when you look at it on the periodic table, has a charge of +3. And oxide, we already know, has a charge of -2. We're going to use the same trick for aluminum oxide as we used for iron 3 oxide. We're going to give our cation the anionic subscript, right? Our anionic charge is -2, so our cation gets a subscript of 2. Then our anion is going to take the cationic subscript of 3. So there's aluminum oxide plus iron metal is just Fe. All right, so this is our chemical equation, not balanced. So let's take a moment to do that. We have, oh, no, sorry, that's our product. We have iron 3 oxide reacting with aluminum metal to produce aluminum oxide and iron metal. All right, now, we've got to balance this situation. So we take an inventory of all the atoms. We've got iron, oxygen, and aluminum on either side of this reaction. Iron, oxygen, aluminum needs an L. On our reactant side, we have two atoms of iron, 3 atoms of oxygen, 1 atom of aluminum. On the product side, we have 1 atom of iron, 3 atoms of oxygen, 2 atoms of aluminum. Now, we need to balance iron, right? So we multiply the product side by 2. This balances iron out. We need to balance aluminum, so we multiply the reactant side by 2. This balances aluminum, and now our, sorry, that looks like a Z. That looks like our equation is balanced. So there's our balanced chemical equation. Now we're ready for part B. So this is part A. Part B. Part B says we have 0.00 grams of iron 3 oxide, and we're asked what is the theoretical yield of iron. And that's another way of saying how many grams of iron will be produced, right? What is the theoretical yield of iron metal? What is the mass of iron produced? So we start with 5 grams of iron 3 oxide. We need to find our mass of iron. So this is going to take some converting. All right. So we go we need a unit conversion to convert from grams of iron 3 oxide to moles. To do that, we need to calculate a molecular mass. I'm actually pulling up a periodic table here. There we go. So we have to calculate this molecular weight. Iron has an atomic mass of 55.845 grams per mole. Oxygen has an atomic mass of 16.00 grams per mole. Now we have 3 oxygens in this molecule, and we have 2 iron atoms in this molecule. So we actually have to multiply these. So 55.845 times 2 is and then 16 times 3 is 48. Adding these two together will give us our molecular mass of iron 3 oxide, 159.69. This has got to be the last sig fig, and it is. All right, so now we can plug in our molecular mass. 159.69 grams per mole. And now grams of grams of iron 3 oxide cancel grams of iron 3 oxide. Next step, we need to convert from moles of iron 3 oxide to moles of iron. And here we get our ratio straight from our balanced chemical equation. 1 mole of iron 3 oxide produces 2 moles of iron. So moles of iron 3 oxide cancel. Finally, our last step, we need to convert from moles of iron to grams. And because iron is not a molecule, we can just pull this straight off of the periodic table. 1 mole of iron will have a mass of 55.845 grams. So Robs, so the values that I am using for iron and oxygen, I'm pulling straight off of a periodic table. You always wait to round till the end of the problem. If you're using a different periodic table, one that has more, that's what I'm looking for, decimal places for their atomic masses, don't round them, just wait till the end of the problem. But that was what my periodic table read, so I'm just going off of that. All right, now moles of iron cancel moles of iron, and we're ready to crunch some numbers. So we have 5 divided by 159.69 times 2 times 55.845. So my calculator is giving me a long number, 3.4970811. I can only have, let's see, we're limited here by our mass is 3 sig figs. So we have to count off our first 3 sig figs. This will round up. This is 3.4. Oops, sorry. That 7 rounds that 9 up to a 10, which rounds the 4 up to a 5. So this is 3.5. But we still need 3 sig figs, so we got to throw a 0 on there. And this is grams of iron metal. All right, so this is now the theoretical yield for iron. All right, that is the theoretical yield. Now, I want to take pause for a minute and look back on the original problem. You'll notice there's a part E, right? A balanced chemical equation. Part B, determine the theoretical yield of iron metal if there's 5 grams of iron oxide that reacted completely. There is a part C to this problem, but I was holding off till now. You may be wondering what's up with this whole theoretical yield thing, and we'll talk more about it in a moment. Part C to this problem says the following. Let me find it in my notes. There we go. Determine the percent yield for this reaction if the actual yield was, let's see, where did I write that? 3.28 grams of iron. All right. You'll notice that we just calculated our theoretical yield, and now I'm throwing 2 new types of yields at you. Something called a percent yield, and then something called an actual yield. All right, percent yield and actual yield. What are these things, and how do they relate to the theoretical yield? Let's break them down, and then we'll come back and do this last part of the problem. So, okay, so first off, the theoretical yield tells you this is the theoretical maximum. The max amount possible. You cannot produce more than the theoretical yield. That is the maximum amount possible. The actual, so your actual yield is the amount, oh, I just realized I'm missing an N up here. The amount actually produced. In the reaction. All right, and the percent yield, and this is one percent yield is an equation that you'll want written down on your exam sheet. The percent yield is equal to the actual yield divided by the theoretical yield. Multiplied by 100. All right, so you take a ratio of the actual over the theoretical and multiply it by 100. The way to think about the percent yield is it's a way of rating the reaction. How efficient was it? How productive or fruitful did you find, or was the reaction? You do this by taking the ratio between the actual and the theoretical. Sorry, I don't know if you can hear my my 2-year-old running around like a crazy person outside. I'm just going to go ask them to play a little quieter. I'll be back in just one sec. Alrighty. Okay, so hopefully that'll tone things down a little bit. Okay, so we've just discussed our theoretical yield, our actual yield, and our percent yield. Let's take a look at that part C. So part C says determine the percent yield for this reaction. If the actual yield was 3.28 grams. Now, you'll notice that we're given our actual yield. .28 grams of iron. And in part B of the problem, we actually we found our theoretical. All right, we found our theoretical yield, which was 3.50 grams of iron. All right, so part C didn't give us the theoretical yield, but we found it in part B, and we're going to use that value now as we calculate our percent yield, which is 3.28 grams over our theoretical, 3.50 grams times 100 divided by 3.5. So my calculator is telling me that I have 93.7142857. I have 3 sig figs in my numerator, 3 sig figs in my denominator, so I can keep 1, 2, 3 sig figs. This one is going to round down, giving me a percent yield of 93.7. And that is the answer to part C. That is the percent yield for this reaction. All right. Okay, so stoichiometry involves balancing chemical equations, calculating theoretical yields, calculating percent yields. All standard fare and things you want to practice and get good at. The next thing is probably the most challenging topic in stoichiometry, and that is the idea of the limiting reactants. All right, the limiting reactant. You run into limiting reactant problems with examples like the following. Nope, we've got one more level. That was actually, you thought it was the final boss, but then there's a surprise final boss right here at the end. This is the final boss for stoichiometry. So all of the problems that I've shown you up to this moment, I've given you the amount of reactant, and I've asked you how much product will be produced. What if you ran into a situation like the following? I'm going to, for the sake of time, give you the balanced chemical equation, though I could totally ask you to balance this, and hopefully you could. You've already done this one, though. This is the combination reaction, right? Combination of hydrogen and nitrogen to produce ammonia. Oh, wow. That 3 looks like a B. There we go. To produce ammonia. Okay, now, if 1.679 grams of hydrogen are mixed with 2.780 grams of nitrogen, how many grams of ammonia are produced? All right, and this is the theoretical yield. All right, what is the theoretical yield? Now, this problem is different than any other problem that I've done before. As I mentioned, if I had told you, oh, you start with 1.679 grams of hydrogen, how much ammonia do you make? You could do that problem. If I told you start with 2.78 grams of nitrogen, how much ammonia do you make? You could do that problem as well. This problem is different, all right? This problem is different because we do not know what the limiting reactant is. Now, think about it. In this scenario, you got hydrogen reacting with nitrogen, and one of them, when one of these two reactants runs out, the reaction's going to be over. The reaction stops when either nitrogen or hydrogen are gone, when they are completely gone. One of these will run out first and leave excess of the other reagents, all right? So in this scenario, when you're given two initial quantities, there is an excess reagent and a limiting reagent. And you need to determine which is the limiting reagent in order to solve this problem, because the limiting reagent, the reactant that runs out first, will determine the theoretical yield of your product. All right? Here's the way to think about it. All right? Here's kind of the mental analogy to give yourself. You're sitting there eating chips and salsa, right? Chips and salsa. One of two things is going to happen. You either run out of chips, and you've got some leftover salsa, or you run out of salsa and you've got a dry bowl full of chips. Doesn't matter which one runs out first. Either way, whenever one of them runs out, you're done eating chips and salsa. You either have to drink a bowl of salsa or eat a, like I said, a dry bowl of chips. But chips and salsa is over. That's the way reactions are. That's the way limiting reactant problems are. You need to figure out, do I run out of chips first or do I run out of salsa? Am I going to run out of hydrogen or am I going to run out of nitrogen? Now, if you're wondering, how do you answer that? How do you determine whether you run out of hydrogen or nitrogen first? You might be wincing because you think it's going to be painful. It's actually not as bad as it sounds. What you have to do is you have to calculate how much could be made with hydrogen. So do a stoichiometry calculation for H2. Then calculate how much could be made with nitrogen. Do a stoichiometry calculation for N2. And then whichever value of NH3 is smaller, that is your theoretical yield, and it came from your limiting reactant. So a limiting reactant problem is essentially just double the work, all right? It's the same calculation, you just have to do it twice, one for each reactant, and then you pick whichever value is smaller. All right, so let's start with hydrogen. We have 1.679 grams of hydrogen. That's our initial amount. And we need to convert from grams of hydrogen to moles of hydrogen, right? And the molecular mass for hydrogen is 2 times the mass of one hydrogen atom, so 2.016. And grams of hydrogen cancel. Next, we need to convert from moles of hydrogen to moles of ammonia. This ratio, the mole to mole ratio here, you get straight out of the balanced chemical equation. 3 moles of hydrogen produce 2 moles of ammonia, so moles of hydrogen cancel. Finally, we need to convert from moles of ammonia to grams of ammonia in order to determine, well, it doesn't determine our theoretical yield. It might be a theoretical yield. We have to do the second half of the calculation before we can make that determination one way or another. All right, so to do this, we need to calculate on a molecular mass. Nitrogen is 14.0 grams per mole. Hydrogen is 1.008 grams per mole, but we got to multiply this number by 3. All right, 1.008 times 3 is 3.024 plus 6, no, not 16, 14.01. I'm so used to doing oxygen. My brain just wants to hit it with a 16. So this comes out to be 17.034. Our last sig fig here has to be in the second decimal place. So this molecular weight has 4 sig figs based on the periodic table I'm using. All right, so we can add this in now. There are 17.034 grams of ammonia in 1 mole. And again, this number has 4 sig figs. All right, moles of ammonia cancel moles of ammonia. And now we're ready to crunch our numbers. 1.679 divided by 2.016 times 2 divided by 3 times 17.034. Whoops, sorry. 17.034. So this comes out to be, let's see, and we can keep 4 sig figs here. 9.458 grams. So that's NH3. Now, what is this number? Well, it might be our theoretical yield. We don't know. We have to do this calculation for H2 and N2, and then whichever value is smaller, that will be our theoretical yield. So we're halfway through, but we have to repeat this calculation with our initial quantity of N2. So starting with 2.780 grams, first we got to convert from grams of N2 to moles of N2. The atomic mass of nitrogen is 14.01, so 2 of them will be 28.02. Grams of N2 cancel grams of N2. Now that we've converted to moles of nitrogen, we need to convert to moles of ammonia. So we put moles of N2 in the denominator and moles of NH3 in the numerator. This is a 1 to 2 molar ratio. 1 mole of nitrogen produces 2 moles of ammonia, so moles of nitrogen cancels. In the final step, we convert from moles of ammonia to grams of ammonia. And the cool thing is, we've actually already done this calculation up above. We know that 1 mole of ammonia has a mass of 17.034 grams, and that this number is 1, 2, 3, 4 sig figs. All right, so moles of ammonia cancel with moles of ammonia. Now we're good to crunch our numbers. All right, 2.78 divided by 28.02 times 2 times 17.034. And we can have, again, 4 sig figs. So our answer comes out to be 3.380 grams of NH3. All right. Now we can make our assessment. Theoretically, if H2 was our limiting reagent, 9.458 would be our mass, or our theoretical yield. But N2 gave us a smaller mass of ammonia. So this is our theoretical yield for this reaction. Our theoretical yield is 3.380 grams, and nitrogen is the limiting reactant, all right? Otherwise abbreviated as LR. Okay. All right. So this is the final boss, right? This is the max level stoichiometry problem. I have another example, but I'm going to write it. I don't think we have time to finish it, so I'm going to write it up. You can give it a try. We'll resume with this example on Thursday. So you can attempt it then. So let me write it up, take a crack at it, come back to lecture, and you'll see if you got the correct answer. All right, so hydrobromic acid reacts with sodium carbonate to produce sodium bromide let's see, sodium bromide, carbon dioxide, carbon dioxide and dihydrogen monoxide. Part A. Write a balanced chemical equation for this reaction. Part B. Part B. Determine the theoretical yield of carbon dioxide if 1.00 grams of hydrobromic acid are mixed with 1.00 grams of sodium carbonate. Part B. Sorry, that is Part B. Part C. The actual yield of carbon dioxide the actual yield of carbon dioxide was 0.222 grams of CO2 or carbon dioxide. Oh, I already said carbon dioxide. The actual yield was 0.222 grams. What was the percent yield? This problem that I've just written pulls together everything that I just discussed, that we talked about in this lecture. Theoretical yield, percent yield, actual yield, and limiting reactant. So this is the Omni problem. This is boss mode. Give this a shot. See if you get the correct answer. We'll solve it together at the beginning of lecture on Thursday. All right? I'll catch half of you in lab tonight in about 15 minutes or so. At 6:45. Yeah, which is about 15 minutes. Anyways, the rest of you, I'll see everybody in 48 hours. Take it easy, dudes.